Welcome everybody. Let's get started. This recitation would be on dimensionality reduction, specifically PCA and kernel PCA. So first, what we mean when we are talking about dimensionality reduction, specifically linear dimensionality reduction. We have a data set X. This data set consists of n examples, and each example is of dimensionality d. So the notation here might be different from what we have seen before in regression, for example, where rows are examples. Here, columns are examples. And we would like to represent this large matrix X as a product of two matrices. The U matrix is a D cross K, where K is supposed to be much lower than D. And Z is a K cross N matrix. So from now the number of dimension point of view, this multiplication should result in a D cross N matrix. If we look at each column of this matrix, Zi, we can think of each column as some representation of Xi, but in K-dimensional space rather than a D-dimensional space. So it's a lower dimensional representation of Xi. And there is some linear transformation. I will call it C transpose, such that Zi is C transpose Xi. And also, we would like to have a way to reconstruct back our original Xi from Zi. We won't be able to do that perfectly, but let's say approximately there is some transformation, linear transformation, and I will call it U, such that approximately Xi is equal to UZI. Okay? If we look at this matrix representation, we can easily see that this matrix U and this matrix U are the same, right? So each Xi is equal to UZI. And if U is an orthonormal matrix, then this is also U. Basically, if you multiply U transpose by U, you will get an identity. And so Zi is indeed U transpose Xi. So, okay. Now there are like various kinds of dimensionality reduction techniques. And basically, their difference is like what's the criteria of finding the best U and Z factorization. And the one that we have seen in the lecture is principal component analysis. And the criteria for principal component analysis is that we want to find U and Z such that I can reconstruct X with minimal error. And so we will go into that with more detail, but before we do that, why would we do this kind of dimensionality reduction thing? So we are replacing our X's with a lower dimensional Z, and that would help us from like computational and the storage efficiency point of view. Also, like we have seen that like sample complexity for supervised learning depends on the number of features. And so if you reduce the number of features, you require less samples. It's also useful for interpretation and visualization. So if I give you a bunch of 100-dimensional examples, it would be difficult to like look at the data, understand the structure, the clustering, these sort of aspects. But if you do, for example, PCA, you can project them to a two-dimensional space. And if you're lucky, you can get patterns like that the data is clustered into, looks clustered into 3 groups, for example. Even if we are not doing machine learning, dimensionality reduction can be used as a compression mechanism. So for example, the face data that we've seen, like if you have n faces, rather than storing the exact image of each face, you can do PCA. That PCA will get you a lower dimensional representation of each face. Each image will be represented by k numbers rather than d numbers. And k could be as low as 10, whereas d could be like 1,000. And all you need, and rather than storing all faces, you need to store what we have called the eigenfaces. You need to store the U matrix so that you can reconstruct a face given its lower dimensional representation. So, in a nutshell, we have data X. Okay? We figured out U. From that, we can compute Z equals U transpose X. And we can keep the Z as a lower dimensional representation of the data. If we have a new data point that was not in our data set, so let's call it Xi, we can still find a lower dimensional representation of that new point using the U matrix that we already learned. Now we can build our classifiers, our clustering algorithms, all our inference algorithms on the lower dimensional Zs. If we store the lower dimensional representation and we want to go back to the full dimensional representation, we approximate Xi as Uzi. Okay? So, yeah. So let's start with PCA. And assume our full, because we are doing this on a blackboard, we want to compress two-dimensional data point into a one-dimensional data point. And so we have a bunch of examples. Okay? Each example is two-dimensional. And we want to represent each example as a single number. And we will assume that the examples have 0 mean. So the data is centered around 0. And we want to find that representation. We want to find Zi is equal to U transpose Xi. Okay? So in this case, U would be a vector. We are searching for a vector that is like a direction in the two-dimensional space, such that the component of the data, of each data point along that direction is a good representation of the data point. So one criteria could be that the difference between xi equals to uzi, the difference between the reconstructed x and the true x has to be minimized. So that means like by doing the compression, we lose as little information as possible. Another way to look at it is that the data doesn't vary that much along that direction. Most of the variance is along that direction, right? And so if we know the component of each data point along that direction, we don't lose much. We explain most of the variability in the data. So we have max variance and minimum reconstruction error. So we want to maximize the variance. So maximize the sum over all data points zi squared, right? Because we assume the data has zero mean, that would be the variance, the sample variance of the data, the sum of zi squared. Okay? Zi is a single number. The variance of all zi's in our data set is just the sum of zi squared. Of course, divided by n, but it doesn't matter. And that's equal to okay. And I will write this as to understand how this follows from this one, we can write this as sigma I equals 1 to n, and then u transpose xi transpose u transpose xi, which in turn is equal to let me write it this way. Sorry. Yeah, sorry about that. I should do that. I should do it from here. So x transpose x this is a matrix such that x transpose xij is equal to xi transpose xj, right? no. Let's do it this way. And then that will be equal to okay, I'm sorry, never mind. I'll send you a note like how this follow from this. Let's continue. So we want to find the direction, and the direction is basically a unit vector. Because otherwise you can choose u to be arbitrarily large, and this objective will grow indefinitely. And so we want to maximize this such that u is a unit vector. Okay, if you want to maximize a function subject to an equality constraint, the way we do it is that we use Lagrange multiplier. So we write the function as the Lagrangian objective as the function we want to maximize. Minus the quantity we are constraining to be equal to a constant. So this represents our constraint, and we multiply it by a Lagrange multiplier, which I think is covered in a previous station. And then, if we take the gradient of this, if we differentiate this function with respect to u and set the derivative to 0, well, the derivative of u transpose u is equal to u. That's the gradient of this function. The gradient of this function with respect to u is equal to 2u. And the gradient of the function like u transpose cu is equal to 2cu if C is a matrix. And so if we use these rules in here and we take the derivative this with respect to u, we get x transpose x u minus 2 lambda u. And we set the derivative to be 0, then we can write this as x transpose xu is equal to lambda u. Okay, and so that tells us that the direction u that maximizes the variance has to be an eigenvector of the covariance matrix x transpose x. Actually, it's x transpose, that's why. That's why I had trouble figuring it. So in this notation, the covariance matrix is x transpose. Okay, so it has to be an eigenvector. Which eigenvector? Well, let's see. Okay, so now we know that u is an eigenvector. Now, like if this matrix x transpose would be a d equals d matrix, and so it will have d eigenvectors. So there are d eigenvectors to choose from. Let's see what happens if we choose the ith eigenvector. Let's call it ui. So what will happen to our objective? It will be ui transpose x then x transpose ui. Since ui is an eigenvector of this matrix, then we can substitute this part by lambda ui, right? But we know that ui is a unit vector. Then ui transpose ui is equal to 1. And so the result is lambda. And so the variance that results from the variance of zi that results from choosing a particular eigenvector is the corresponding eigenvalue. And so if you want the maximum variance, then you would choose the eigenvector corresponding to the maximum eigenvalue. And so the algorithm so far looks like this. Construct the covariance matrix. Pass the covariance matrix to your favorite eigenvalue decomposition algorithm. Pick the top eigenvalue and the corresponding eigenvector. That eigenvector is your linear transformation. So now we are assuming k equal to 1. If you want to map a data point to that low-dimensional representation, compute u transpose xr. Given a low-dimensional representation, you want to recover the original data point, multiply zi, which in this case is a scalar, by u. Okay? We said we have two views. This is the maximum variance view. The other view is the minimum reconstruction error. We want to find u such that xi and xi tilde are as close as possible. What I'm going to show now is that these two views are equivalent. I'm going to show that first algebraically and then geometrically. So we have an xi. That's the original data point. And we we want to compare it to a reconstructed version. That means we apply U transpose to xi, so we put it in a lower dimensional space. So for example, let's call this point xi, and let's call this one would be xi tilde, which is mu multiplied by zi. So zi to be have things visualized. The z is the distance along that line. Like, so this is our training point. The z is basically the magnitude of its component along the direction u. And so it's a single number. If I multiply zi by u, I have a two-dimensional vector which I call x tilde. And so I want to minimize the difference between these two. So that's equal to okay. And then minus 2 u transpose xi multiplied by u transpose xi. And then finally, these two terms plus u transpose xi squared times u transpose u. Just expanding this inner product. So you can easily see that this is a this doesn't matter with respect to u, right? If these are the u transpose u is equal to 1. So the net result would be minus sigma I u transpose xi whole squared. Which is like the same objective that we started with in the maximum variance case, but with a negative sign. So that means maximizing the variance and minimizing the distance are exactly the same problem. And geometrically, as you have probably seen that in the lecture, if we have a point xi and we have a projection which is equal to, this is Ci, then by Pythagoras' theorem, xi squared is equal to Ci squared plus, let's call Ri for residual or error, plus Ri squared. And since this is constant, then maximizing Zi is the same as minimizing Ri. If you take the sum over all data points, so this is a single data point. Right? If you take the sum over all data points, then this is summation Zi squared, which is the variance. and this is summation Ri squared, which is the mean squared error. And this is not just for PCA, like usually even for linear regression or any other algorithm that deals with that tries to minimize mean square error, you will find this kind of duality or equivalence between minimizing the square error, the square difference between your prediction or your reconstruction and the original data, and maximizing the variance of your output. Usually it's termed explaining the variance in the data. Okay, so now we are able to find a single vector U. Now we would like to find multiples of these U's so that we can have a low dimension representation of dimensionality k rather than dimensionality 1. So what we do, unfortunately, for this for two-dimensional data, only you can't go beyond two vectors. But anyway, what would be the second direction if I want? So I now choose this direction to maximize the variance or minimize the square error, the reconstruction error of our data. The second direction, first, I argue that it has to be orthogonal. Because, as we can see here, the error is orthogonal to the component that you used for your representation, right? I mean, if you use a particular direction U to to project the data into a lower dimensional space, the error between your projection and the actual data point is orthogonal to that, right? And so if you want to reduce that error, you have to choose there's no need to choose a direction that's not orthogonal to your first direction. The error has no component in U. Is that clear? The error after projection is orthogonal to your projection subspace. And so if you want to reduce that error, there is no need to have a component that's not orthogonal. Okay? And so, okay, it will be an orthogonal direction. In 2D, there is one orthogonal direction, and that's it. But if you have multiple dimensional data, which is the typical case, which orthogonal direction to choose? Well, again, the direction that maximizes the variance of the data. And so it will be an eigenvector of the covariance matrix. The same reasoning applies. But now, rather than choosing the first eigenvector corresponding to the largest eigenvalue, we will choose the second eigenvector corresponding to the second eigenvalue. And so finally, the principal component analysis is that you do eigenvalue decomposition of the covariance matrix once, and you pick the eigenvectors in the decreasing order of eigenvalues. Okay, how many eigenvectors should we keep? If you want to set the reconstruction error to 0, then you'll have to keep all the d eigenvalues and the d eigenvectors, which is okay, but that means you didn't do any dimensionality reduction. You just did change of axes. basically, you choose the eigenvectors as long as you keep adding eigenvectors as long as the remaining variance is not too large. How to assess the remaining variance? Well, we have already shown that the variance along a particular direction is given by the eigenvalue. So you have the first eigenvalue telling you the variance across that direction. The second eigenvalue telling you the variance across that direction, and so on. And so by examining the eigenvalues, you can tell whether the remaining variance is unnecessary to keep. Okay, is that clear? Any questions? Okay. Now, in practice, what you actually do to compute the PCA? Oops. So, I said that you would compute the covariance matrix and then pass it to your MATLAB eigen decomposition function. But in practice, what could happen is that let's, for example, consider the face data set. So the face data set, let's say we have 100 faces. But each face, the image is 100 pixels by 100 pixels, and that makes it 1,000 dimensional data point. So we have D equals to what? 10,000 and n equal to 100. Now, what's the dimensionality of the covariance matrix in this case? $10,000 to 10,000. That's like 100 million. So we start with a matrix that's 10,000, yeah. And so the point is, basically you might run out of space or store an unnecessarily large matrix. Rather than storing this matrix, you need to compute and store a 10,000 by 10,000 matrix, right? And so what happens in practice is that we don't explicitly form the covariance matrix and then compute the eigenvalue decomposition. We use what's called singular value decomposition. Actually, let me do it over there. Yeah. Okay, so SVD. So the eigenvalue decomposition, if you have a square symmetric matrix like the covariance matrix X transpose, you can write it as U sigma U transpose, where U is like a matrix that consists of orthogonal columns. So this is UI. Right? And sigma or lambda is a diagonal matrix that consists of your eigenvalues on the diagonal. Right? And so another way to look at this decomposition is that you can write XX transpose as summation of lambda RUI transpose, right? And so what we are doing actually in PCA is that, well, we're saying that this summation can be approximated by keeping only the k largest eigenvalues other than all of them. That's essentially PCA, that the variance of the data can be largely explained by a few eigenvalues and their corresponding, by a few eigenvectors and their corresponding eigenvalues. The SVD is the generalization of the eigenvalue decomposition, and it works for any matrix. It doesn't need to be symmetric. And so the way we write SVD is that X is equal to U sigma V transpose. And so again, U is like a matrix of orthogonal columns. I'm here describing what people call thin SVD. In thin SVD, sigma is a diagonal matrix of what's called singular values. And then V transpose is a matrix of orthogonal rows. Okay. What's important about SVD is that the U, which what we also call the left single vectors, is are the same as the eigenvectors of X transpose. And V, these are the eigenvectors of X transpose X. And the singular values, sigma, are the square, the singular values, sigma, are the square root of the eigenvalues of X transpose and X transpose, because both matrices have the same eigenvalues. And the singular vectors are the square root of these eigenvalues. And so in practice, you don't need to build the covariance matrix. You can do SVD of your data matrix, of the original X. And the eigenvectors would be the left singular vectors of the SVD. And you can use that to project your data. And if you want to measure the variance, the singular values tell you that, like this, take the square of the singular values, that would be the eigenvalues of the covariance matrix. Okay? So that's great because we have efficient algorithms for computing the SVD. We have algorithms for computing SVD even if the data does not fit in memory, there are algorithms to compute SVD, like if you read the data from disk or they come online. There's online SVD algorithms that allow you to read the data one by one and update your SVD as you go through the data. So there's a whole body of literature on fast and efficient computing of singular value decomposition. And again, we can reinterpret this matrix equation as a summation of rank 1 products. That means that the matrix X is a summation of vectors UI multiplied by vector VI transpose. And these UIs basically span the range of the matrix X. And so, like any data point has to be expressed as a linear combination of the vectors in this U. That is, if you consider all singular, if you keep all the u's, or all the u's corresponding to non-zero singular values. You can discard singular values, and that's basically saying that, well, the data points that are not within the span of these u's are not important to me. So for example, that's saying if I keep a single u rather than both of them, that's basically saying I don't care much about the variance in that direction. Okay? So I just wanted to go through an example of how can we can we interpret the results of PCA and SVD. And basically, the interpretation will be based upon this notion. So let's consider the Netflix data. So we have movies, and we have users, and we have ratings. Each user rates a movie. And so our data X consists of the movies. The movies are rated by n users. Okay? And so each example is a user, and the features are like the ratings of that user for all movies. And I will consider an idealistic case. It doesn't happen in practice, of course, but it will allow us to kind of like get the intuition of like what SVD does. And so the idealistic case is that I will assume that the data is perfectly clustered, that we have 3 types of movies. And I will call it comedy, action, and documentaries. And we have 3 categories of users. I'm being stereotypical here, sorry, just for sake of the argument. So we have like family-oriented users. We have teens, and we have nerds. Okay? And it turns out that family users watch comedy movies, but nothing else. And teens watch action movies, but nothing else. And nerds watch documentary movies, but nothing else. Okay? So we have like a block diagonal matrix. Each block, like we have blocks of 1s, like watch the movie, and 0 everywhere else. And my question is like, what will happen if we factorize this matrix into like rank 1 matrices, like this? The key point here is that a matrix of all 1s is equal to a column vector of all 1s multiplied by a row vector of all 1s. Okay? So we can actually write this matrix as something like this. We can write X is equal to a vector of all 1s in the first block, 0s in the second block, 0s in the third block, multiplied by a vector with the same characteristics. This is another one with the 1s being in the second block. this is a third example with the ones being in the third block. Okay? So remember, this dimension is movies, right? And this dimension is users, right? And I will call this vector is u1, and this is v1, right? And this is u2, and this is v2, and this is u3, and this is v3. Okay? Of course, this is not technically correct because u and v have to be unit vectors, and so they have to be scaled down to be unit vectors, and that scaling will appear as a singular value, sigma 1, sigma 2, and sigma 3. Okay? But for simplicity, let's just deal with these vectors as they are. Now I have a new user. First, like if you just look at these data, it tells you that, well, users and movies can be explained using three aspects. Like how much comedy in there, how much action in there, how much documented in there. Of course, in the real setting, we don't know the interpretation. We like look at the data and then we try to figure out the interpretation from what we see. But at least we see kinds of like three aspects in this matrix, right? Now, I have a new user. And this user has ratings. What this SVD tells me is that I can represent the ratings of the user approximately using three numbers. How much is aligned with U1? How much is it aligned with U2? How much is it aligned with U3? So I have this new user xi. I will compute U1 transpose xi. And that would be a number. And that number, again, in this interpretation, like how much is this user oriented to comedy movies? It will be some number. Let's call it like 1. And then U2 transpose x1 would be like 3. And U3 transpose xi would be equal to 1. Again, like U has to be a unit vector, but just for illustration, I'm using ones and zeros. And so like this user is more into action. And so I would just need to recommend action movies. Because like if I build, for example, a classifier or whatever system from the data, I just need to use these three numbers. I don't need to build a classifier from that's giving this entire vector, just these three numbers. Okay? Of course, like this data looks clean, but this is basically the idea that like most of the information, the assumption is that most of the information in your matrix actually can be expressed as in like lies within a low rank structure. And the SVD helps you to find that structure. And the product of the SVD is that it tells you like what are the significant components of that structure and how can you map your high dimensional data point to these significant directions. And also how to do reconstruction. So if I have now these three numbers, I can reconstruct x back by, I think like it, so x is equal to like u1 times this component plus u2 times this component plus u3 times this component. Okay? So yeah, when you're thinking of SVD, you can think of this picture of like sum of lower dimensional, or actually rank 1 matrices. Okay, I think we are running out of time, so two quick things. So is PCA the answer? Like, so now you are given a data set, and you want to like do some exploratory analysis. We usually start with PCA. But does that mean PCA is the best thing to do always? No. So what PCA does is that it finds an orthogonal basis through a linear transformation that minimizes the square reconstruction error. And there could be a problem in any of these three characteristics: orthogonal, linear, minimizing the square error. Just give you some examples of like what can go wrong and what should you do in this case. So orthogonal. PCA loves to give a data like this, a basis like this. This is U1 and this is U2. And this is okay if your data looks like this. PCA will work in this case. But what if your data looks like this? So in this case, the data looks like a class. If you run PCA on this data, typically the first direction would be like that direction. I mean, suppose this angle is smaller than this one. It will pick that direction as the maximum variance direction. And then it will pick the other direction would be the orthogonal one. Sometimes you want to actually like track these two directions of the data. So for example, this arises in a problem called blind source separation. Like, suppose you are hearing two people talking, right? And you have two ears, or you have two microphones. And so each microphone receives some weighted combination of the two sources. And so this is what you hear from mic 1, and this is what you hear from mic 2. Okay? And now the objective is not to find directions that maximize the variance. I want to find direction that aligns with the first source and aligns with the second source. That's not necessarily the best direction from the reconstruction error point of view. And so we need to rethink of our objective. And so like the objective in this case, we want the directions to be like, we want data along that direction, data along that direction to be independent because they come from two different sources. And that gives rise to what's called independent component analysis. Another example is if you have outliers, and by outlier I mean like most of your data are concentrated except for a few points. If these few points are far away, they will mess up with your PCA, because the PCA, basically if they are far, that means they will have high reconstruction error. And so PCA, rather than trying to fit the mean stream points, will also try to shift the direction to capture these outliers as well. That's because it uses the mean square error as an objective. And so you need to find another dimensionality reduction method. Finally, if the data is linear, if the data is not like the directions of variance do not lie nicely on like a linear subspace. So if the data looks like this, for example, they are like concentrated around this nonlinear manifold. PCA will attempt to find U's such that U projection is U transpose X. And so it will attempt to find like some mapping that basically increases along a straight line. But you want to find a mapping that like increases along this direction. And so in this case, we can use kernel PCA. Kernel PCA, like kernel SVM, we use the kernel trick to turn a linear algorithm like PCA into a nonlinear algorithm. And the way we do it is, again, like kernel SVM. First, we show that our solution is a linear combination of our training data. This is what happens with SVM. The weight can be written as a linear combination of our examples. Also, in this case, we can show that if we want to minimize the reconstruction error, then or maximize the variance, then U has to be some linear combination of the training examples. Because if U has a component outside the range of your training examples, then there's no variance along that component. And so it doesn't make sense to put weight on something that has zero variance. So the first step is understanding that the solution is actually a linear combination of training data. The second step is to rewrite the algorithm in a way that we just need to compute inner products. And so if our original problem was X transpose X, was X transpose is equal to X transpose U is equal to lambda U. And now knowing that U is equal to X alpha, then we have X transpose X alpha is equal to lambda X alpha. And so this is a common phenomenon in kernel algorithms, is that your solution, you keep only these weights. Like if you have n training examples, your solution is an n-dimensional vector that contains like the weight of each training example in that linear combination. That happens in SVM, that happens in kernel regression, that happens in most kernel algorithms. And so U was like a D cross 1 vector. Here, alpha is an n cross 1 vector. Because we can't keep track of a D cross 1 vector. D can be very large. D could be infinite in kernel algorithms. And so we multiply both sides by X transpose. We get X transpose X transpose X alpha is equal to lambda X transpose X alpha. Now, X transpose X alpha, if you expanded this as a matrix, such that X transpose X ij is equal to the inner product between xi and xj. And so this matrix as a whole can be computed using inner products, right? And so we call it the kernel, the gram matrix, the kernel gram matrix. So we have basically K alpha is equal to lambda K alpha. We will cancel these K with each other. I'm a bit hand waving here, but this is correct. And so now alpha is an eigenvector of K, the kernel gram matrix. And so now U is equal to, like U1 is equal to X alpha 1, U2 is equal to X alpha 2, and so on. Again, if I want to transform a new training point, a new point into a lower dimensional space, I need to compute U1 transpose Xi, for example. And so that would be equal to alpha 1 transpose X transpose Xi. And so that means, so X transpose Xi is the dot product between the new point and all examples. So that would be an n cross 1 vector, and alpha transpose is a 1 cross n vector. Take the inner product of these two vectors. Now you have the representation of Xi in the first principal component. You do the same for U2, U3, and so on. Okay? Any questions? Okay, so that's basically it. The take home is that the main point in PCA is that you can explain the variance in the data using a few dimensional components other than all dimensions of the data. That the PCA gives you like a linear transformation and a basis, orthogonal basis, that you can use to transform the data into a lower dimensional space. And you can then perform all your machine learning algorithms in that lower dimensional space. And if you want to like reconstruct back the data, you can use the same basis to reconstruct back the data in the original space. And you can do that in the kernel version, but in this case, your like basis vectors won't be like explicit d-dimensional vectors. They would be weighted combinations of your training data in the kernel space. And but still, just these weights are sufficient to be able to, I mean, these weights together with the training points are sufficient to be able to transform any new point to a lower dimensional space by doing these inner products. Okay? Questions, concerns? Okay, thanks.